Okay, so welcome to the lesson on chapter 11. Today we're going to be switching gears a little bit. We're going to be talking about quantified predicate logic, which is sometimes called first order logic, and which you'll often hear me just call predicate logic, just for the sake of shortness, I guess. But yeah, let's get into it. It's a little bit of a change of pace, but shouldn't be too much, I don't think. So let's go ahead. So far, as you will remember, we've worked in propositional logic. So all our language has been about the relationship between propositions or claims, right? So, if we have something like if P then R, then that tells us something about the relationship between P and R, where P and R are each a whole claim or a whole proposition. So in our previous schemes of abbreviation, for example, P has represented the proposition or the sentence or the claim, Plato prances. And R has represented the proposition or the sentence or the claim, Remy cooks ratatouille. Right? So that's what we've been working with, propositional logic. But this doesn't let us talk about the relationships of quantities or objects and their features that we might want to talk about sometimes when we're thinking about reasoning, when we're thinking about logic, right? So, sometimes I'll want to talk about qualities where, if we want to say, well, all dogs have fur, then we need to talk about having fur as a property of being a dog or something, right? So we might want to sometimes divide those parts up. Like, what if I want to look at the logical structure of one proposition, one sentence? Every dog has its day. We want to look at its parts, right? We want to look at the parts of that sentence. So far, propositional logic doesn't let us do that because we have to treat that just as one letter, right? Like that would be, I don't know, P could be every dog has its day. So we need a new language that talks about quantities. So every, for example, we want to look at how every dog has its day. Talks about a quantity of dogs. In this case, all of them. We need a new language that lets us talk about types of objects. So we need to name things. In this case, the types of objects we're considering are dogs. Not that animals are purely objects. We're just using the word object to mean like a thing. So like a human could be an object, the color green could be an object, whatever. And we also need this new language to talk about features of those objects. So in this case, the feature is has its day. That's a feature of every dog according to this sentence. Every dog has its day. So we need new language, right, to talk about these things, these parts of the sentence, of the proposition. So as we develop this new language, you'll find that a lot of things stay the same. We're just kind of modifying or adding things a little bit, but a lot of stuff stays the same. So first we need predicates and names. So many declarative English sentences have a predicate and a name, or a predicate and a subject, as you might have heard it called. The name is who or what the sentence is about. So it's what the whole sentence or the whole claim is about. It's the subject of the sentence. And the predicate is what that named thing is doing or has as a feature. It's what we're saying about the subject, about the name. So, for example, if we have the sentence, Alan is tired, then Alan is the subject, Alan is the name, Alan is what the sentence is about. And then is tired is the predicate. It's what we're saying about Alan, right? So for predicate logic, which is now what we're developing with our new language, our atomic formulas will take account of both names and predicates, right? Previously, our atomic formulas were just propositions. They were letters like P or Q or R, and those were to stand in for whole sentences. But we're going to have a new kind of atomic formula for our language that takes account of predicates and names. So we'll have capital letters, F through O in our case, for representing predicates. This is like stylistic because we don't want to get confused with the P's and Q's we've already been using. So we're going to use F through O for predicates. And then we're going to have two types of small letters for names, for our subjects, right? So we'll have constants. This is one type of name for particular named subjects. So for example, if we want to talk about one individual named Alfonso, we will use a constant. We would probably use A for ease, right? Just it's easier to use A since that's what Alfonso starts with. But it could be any particular person, right? It could be Jim. It could be this water cup, right? Any particular object will be referred to with a constant. And then we'll have variables for a name that could be a number of people. So sometimes, if we just want to say he in the abstract without referring to anyone in particular, we would use a variable. And for those, we'll use V through Z, most often X. X and Y are probably our go-tos. But yeah, if we need others, we have access to them. And so, he might be a variable name if we're saying, anytime a guy goes to the mall, he sits in the food court. I don't know. Since we didn't specify who the guy is, it could be any guy. And so he could mean any guy, right? So he in that case would be a variable. We would represent it with some letter V through Z, probably an X. This is a lot to take in all at once right now, but as we go, it will become easier to understand, I promise. Especially once I show you some examples. Okay. Speaking of examples, here we go. So suppose we have a scheme of abbreviation or a translation key like so. You'll see that little a means Alfonso, right? It means one, it's a constant. It's a name for one individual person, Alfonso. And here, little b means Brett. Again, it's a constant. It's a name for one particular person, Brett. Let's just assume there's only one Brett and one Alfonso in the world, which I know is not true. But then we have F, big capital F. It stands for the predicate, is a fisherman. In that case, we're saying that's a predicate, right? That's something you would say about someone. And if we have big G, we'll say, is a predicate, meaning is great, right? And then let's say we want to represent the subject-predicate phrase in our new predicate logic. We want to represent the subject-predicate phrase, Alfonso is a fisherman. Well, we can use our scheme of abbreviation like so. We would end up writing F and then in brackets A. What this means is we take our subject, so in this case, this little a for Alfonso, we wrap it in brackets, and then we stick a predicate in front of it. In this case, F, because F means is a fisherman. So then, F and then in brackets little a means Alfonso, little a, is a fisherman, big F. And this is as basic a claim as our new language will allow. We can't have anything more basic than this in our predicate logic language. This is an atomic formula then, the same way that when we did propositional logic, P or Q or R were atomic formulas. But in this predicate logic language, a subject with a predicate in front of it is as basic a claim as our new language will allow. Okay. We can also represent more complicated phrases in our new predicate language. So if we want to say Alfonso is a fisherman and Brett is not great, right? Well, lucky for us, we're going to keep our same connectives from propositional logic. So we still have our and symbol, we still have our or symbol, we have our not symbol, we have our if-then arrow, and we have our if and only if double arrow, right? So in this case, we'll get F and then little a in brackets. That'll tell us Alfonso is a fisherman, right? And then we have our not G, and then in little bracket B, which says Brett, this little bracket, little in bracket B, is not, with the not symbol, great. So this comes out saying Alfonso is a fisherman and Brett is not great. So I hope this is starting to make sense, right? And so at that point, we'll have subjects, we'll have predicates, great, but you'll remember way back when we were talking about the features our new language has to have, we also wanted quantifiers. So this is where things change up a bit more, I would say. All right. So we need to consider English words like some and all, right? Those are the two predicates we're going to have in our predicate logic language. So we're going to have to introduce quantifiers, symbols that represent quantities, right? So we're going to have this universal quantifier, which looks like an upside down A. And this will be, it'll mean like all or every. It's universal in quantification, right? It's quantifying an amount of all or every, a universal amount, right? So that's it. That's the upside down A. It's our all symbol or our universal quantifier. Then we're going to have the existential quantifier, which looks like a backwards E. And this is going to represent words that indicate the existence of something. That's why it's called an existential quantifier. So it'll say there is or something. But most simply, and I'm going to try and use this all the time because it makes things clearer, it's going to represent an amount of at least one. It just says, at least one. There is at least one. That's what this existential quantifier is going to end up saying. Okay, so those are our two quantifiers. We have this upside down A that means all or every, and we have this kind of backwards E looking thing that will mean at least one. Right. There is at least one. So I'll show you some examples. So we're going to keep the same scheme of abbreviation with Alfonso and Brett and is a fisherman and is great. But now we can add in our quantifiers, right? If we want to talk about things in general, right, we need to use variables, though. Oh, right. Sorry, I sped through that too fast. With our quantifiers, though, we're going to talk about things in general. We're not going to be specific about one person normally, right? So we're going to use our variables v through z. You see I started at x here because we're almost always going to start at x. And we're going to use our variables instead of our constants like Alfonso and Brett. I've left them up here because this is our scheme of abbreviation, but you'll see we're going to use our variables instead here. Okay, so let's look at translating some quantified phrases. So, for example, if we want to say all fishermen are great, right, we would end up writing, for all x's, for all things, right? This is a variable, so it's non-specific. If it's a fisherman, it's gonna be great. If it's a fisherman, then it's great. So you can see, since we're talking about a variety of things here, we're not talking about just Alfonso or just Brett or just whoever. We're talking about, everything. If it's a fisherman, it's great. So in this case, we have to put our all qualifier at the front here, our all quantifier, universal quantifier over here. And then everything after it goes in brackets, right? Because it's talking about all fishermen having to be great if they're fishermen. So the claim here is, we have this little x, could mean anyone. And we're saying if it's a fisherman, then it's got to be great. That same x has to be great. Right? So that's how you would translate something like all fishermen are great. Similarly, if we want to say there is at least one fisherman who is also great, which is just a claim that there's one person, but it could be anyone, but there's just one person, there's at least one person, could be anyone, who is both great and is a fisherman. We're not saying, well, if they're a fisherman, then they're great. We're saying there's at least one person who is a fisherman and who is also great, right? So we're going to translate that with our existential quantifier, right? So this says there's at least one x, and then we're going to wrap the whole rest of the sentence in parentheses here. There's at least one x where that x is both a fisherman and that x is also great, right? So then we have there's some x who is both a fisherman and is great, right? But because this English claim is not about, one specific person, it's just about some vague fisherman who is also great, then we use this variable x instead of our constants a or b, right? Yeah, okay. So yeah, notice how the brackets surround everything we're discussing with the quantifier, right? Because, for example, in this, there is some fisherman who is also great claim. We're using the quantifier to discuss this one X who is both a fisherman and is great. So it goes in front of that bracket and it modifies everything in the bracket. Same thing up here with our universal quantifier. Okay. Yes. So as we go, you'll notice that we only use quantifiers to talk about variables. Quantifiers never modify constants because, you know, if a constant points to one individual named thing like Alfonso or Brett, well, we don't quantify over that, right? There's no reason. If we're making a claim about Alfonso, we don't need to say all Alfonsos do X or there's at least one Alfonso who does X because we're just talking about Alfonso, right? It's just the one person. So when we use quantifiers, we're only going to be only using them to talk about variables, some non-specific thing. Okay. And then a quick side note as we go forward, when quantifying something, we're going to use the actual letter A, X, instead of the upside down A, X. And we're going to use the actual letter E, X, instead of the backwards E, X. And this is just because we're doing everything on a computer, right? So in Carnap, you can also use the A, capital A, instead of the upside down A. And we're going to do this because it's easier to type A than to put in the Unicode for an upside down A. And similarly, it's easier to type a capital E than to put in the Unicode for this backwards E quantifier symbol. But you should just remember the real symbols, the upside down A for the universal quantifier and the backwards E for the existential quantifier. So that if you ever have to handwrite any logic in the future, or if you're ever reading anything with logic in the future, or if you're using logic in a system that doesn't take A and E, you will know the real symbols, which are the upside down A and the backwards E. Okay. All right, so another quick side note. In chapter 11 of the textbook, you're given a bunch of details about scope and binding in our new language. And really, I don't think we need to focus on those too much, which is what I'm going to say in the next slide, actually. But I mean, I'll go over them quickly, and I'll tell you after why I don't think we need to focus on them too much. Okay, so a quantified phrase has a wide scope if the quantifier in that phrase quantifies everything in the phrase, right? So for example, we have, for any X, for all X's, if it's an F, then it's a G as well. If X is an F, then X is a G. In this case, we can see that the quantifier is ranging over everything in the phrase, right? All of this is in the brackets right after the quantifier, so the quantifier is ranging over everything. But a quantified phrase can also have a narrow scope. If a quantified phrase has a narrow scope, it does not quantify everything in the phrase. So in this example, we have all X's are F's. If all X's are F's, then there is some Y, which is B, right? And in this case, the all X quantifier, the universal quantifier, is ranging only over the X's and F. It's not ranging over this because you can see the brackets only contain the X's and F. So the universal quantifier here, the all X, has a narrow scope. And similarly over here, there's an existential quantifier for a Y. And it's ranging only over the claim that Y is B. So in this case, the existential quantifier here, there is at least one Y, which is B. There's some Y, which is B. It has a narrow scope as well. It only talks about this. Neither quantifier here talks about the whole phrase, right? It's not ranging or quantifying the whole phrase. Now, we're almost always going to be looking at sentences with wide scopes, where all the quantifiers are just at the front and they range over everything. But yeah, it's possible that you have a quantified phrase where quantifiers have narrow scopes. Okay. And then binding, yes. Okay. So a quantified phrase binds a variable if the phrase has that variable in its scope and no other phrase within the first phrase's scope has that variable in it. So really, we're not going to focus on that too much. This is just a way to know which quantifier is modifying a variable, right? So, in this case, let's go back up here. We have this all x's. If they're f, then they're g. If all x's, if they're f, then they're g. In this case, the all x binds the x in both cases because it's within the main phrase's scope, it's within the all x's scope, and there's no other quantifier inside this phrase that modifies the x's. So it's just telling you like where the x's are getting their quantification. Well, they're bound to this ax over here. But again, we won't be talking too much about sentences that are complicated by that. So I wouldn't focus on them too much. I say here, you read the scope and binding details in chapter 11. I would if I were you. But we're already in the last couple classes of this course, so we don't want to cram too much in and confuse everything. And our problem sets don't really have examples that are significantly impacted by those specifics. So we'll skip them for now, but you should read them. You should know them. It's possible they impact a question on the final exam, but I wouldn't worry about them too much. Okay. Another note about quantifiers. So sometimes there will be multiple quantifiers quantifying multiple variables in a phrase. So, in this case, I'll give you an example. We could have this phrase, and this is saying, for every x, that's what this is saying, and for every y, either the x's are fishermen or the y's are great, right? So we might say, yeah, I guess that's the best way of reading that. But the point is that, these quantifiers, we could have multiple of them in front of a phrase, impacting various objects in the phrase. I should probably get rid of this parenthesis. Anyway, the point is that, when you see multiple quantifiers at the beginning of a phrase, they're modifying what is inside the phrase. So in this case, we have all x's, which means that when we have an x here, we're talking about all x's are f's, or it's the case that all y's, you can see the y's being modified here, are g's, right? So there could be multiple quantifiers at the beginning of a phrase modifying everything inside of it. Okay, good. So now I will show you some Carnap practice where we do some predicate logic translations. Chapter 11 has problem set 15 in it, which is tied to this video, right? So in problem set 15 in chapter 11, it's interspersed throughout the chapter. You'll be doing simple translations throughout, but I'm giving you a practice document with translations on it, and I'll go over some of them, which will look more like the translations on the final exam. Okay, good. So I will show you some Carnap examples. Okay, so as always, I'm showing you where the practice is. It's on lesson 11. You can see on the bright space here, it might look a little different for you as always, but it's there. And you can see on the right side of the screen, I've already copy and pasted into my notes the translation key we'll be using. So let me just, yeah, here we are. So we're going to do some predicate logic translations together. And we'll start with some of the first ones. We'll do a few of the first ones, and then we'll do one of the harder ones, and then I will leave the rest of the practice to you guys. Okay, so let's start. So we have this sentence, everything has a smile, right? And we can start translating it in our notes like we normally would, right? So we have the sentence, everything has a smile. And just like normal, we look for stylistic variations. I guess we kind of have one with this everything. So we'll just say, you know, well, everything works fine here. We don't even need to change it. And then we go has a smile, right? So we're looking at has a smile here. And you'll notice that there's no connectives. There's really no stylistic variations besides kind of this everything, which we could say is all or whatever. So we can get straight to translating. There's no connectives here, nothing. We can substitute in what we have. Great. Well, we have this everything quantifier, right? And we know that that's a universal quantifier. It's saying everything has a smile. So we know that we're going to start with this quantifier. And it's saying everything has a smile, right? Well, this is a predicate, has a smile, right? And then we'll look to our translation key. We see, oh, has a smile is represented by O. So we'll use O. And of course, we have to bracket it off from the quantifier. And what are we quantifying? Well, everything. It's a vague thing. It's not a constant. It's clearly not Carl, Egbert, or Betty. So it's a variable. It's not a constant. So we put in a little x. We close all that up, and we have here, for all x's, x is O, which means for us, for everything, it has a smile. X has a smile. So we'll copy that, stick it in our Carnap practice session. Again, you should do the problem set in chapter 11. This is just a practice document you can do. Hit enter, and we'll see perfect match. That's great. Okay. Obviously, this is a practice document, so you can't submit. It says this document has not been assigned, and that's true because it's a practice document. Okay. So now we want to say nothing has a smile. Okay, so this one could be a bit trickier, right? So let's copy that into our notes. Maybe you're doing this on pencil and paper. I don't know. Anyway. So luckily we have no real stylistic variance except for maybe this nothing. And what is nothing saying? Well, it is saying it is not the case that anything, not the case that even one thing has a smile, right? The nothing there is not saying not all things have a smile, because that could mean something could have a smile even if not all of things do. It's saying there isn't even at least one that has a smile, right? So we would say, we could put this as it is not the case that at least one thing has a smile, right? This is saying it's nothing. Nothing has a smile. So let's translate that first. So we would get not at least one thing has a smile. And then we know has a smile is again O. That's the predicate. And again, we're not talking about any constants. We just have a variable because we're not talking about any specific thing. So we're going to say no, there is nothing that has a smile, right? So let's copy that. Let's put it in here. And let's check our answer. And there we go. It's a perfect match. It's a perfect match. Okay. So great. So those are like basic ones. You can see we just have a predicate here. Okay, so let's do this one. So in this one, you'll see there's no quantifiers. We don't have a claim about everything or all things or at least one things or some things. We're just talking about Carl and Egbert, right? They're just the two names. So we don't have any quantifiers. If Carl doesn't have a smile, then neither does Egbert, right? So, well, let's look at stylistic variations. So we have if Carl doesn't have a smile, then neither does Egbert. And in the main connective here is if then, it doesn't need to be translated at all. But we have this doesn't and this neither. And those are clearly stylistic variations of the negation symbol, right? Of not. So let's do those nicely. So let's separate our if-thens, and then we have if it is not the case that Carl has a smile, then it is not the case that Egbert has a smile, right? Great, so now let's translate the main connective like normal. So we have a if then, so we'll put an arrow there. Great, and we'll put brackets around our parts. Good. All right. So now what do we have here? Well, we have two more connectives. We have a it is not the case that, and we have a it is not the case that. So let's translate those. Put a negation symbol. And then we have our subject predicate statements. First, we have Carl has a smile, and we have Egbert has a smile. So how do we translate those? Well, we look at our translation key, our scheme of abbreviation, and we find the Carl is, or let's do the predicates first. So we have has a smile in both cases. So we'll put an O. We'll put an O. Egbert has a smile would be O. And then we have Carl and Egbert left. So Carl is represented by a little c, and we're saying he has a smile, so we'll put him after the O and put brackets around him. And Egbert is represented by a little e, so we'll put an e after the O on this side. Little e surrounded by brackets. And there you go. You can see we have if Carl does not have a smile, then Egbert does not have a smile, right? So let's copy that. Let's stick it in. And there you go. Perfect match. Look at that. Okay. So let's see. What else can we do here? Let's do a more complicated one. Let's do some good humans go to Halifax. Let's do that one. Why not? So in this case, we have some quantifier here, right? We have some. So that means at least one, right? Some is the same as our existential quantifier. It means at least one. And we know anytime we introduce a quantifier, it has to be talking about a variable. So we'll just use a variable x there. Good. Okay. So we have some good humans go to Halifax, right? So what are we saying? Well, we're saying, you know, if there is an x, right? There is at least one x where if it is a good human, it goes to Halifax, right? Or there is some x which is a good human and which goes to Halifax. That's probably better. So let's write that out. So we would write, you know, if there's an x, and let's block this off just for sake of ease. So there is some x who is good and who is a human. Well, what do we have here? Is good is represented by G, and is a human is represented by M. So let's say, you know, if there is an x, or there is an x which is good, and that x is also human. Oops, this needs to be a little x. Okay. So we are saying, as you can see, there is at least one x who is good and who is a human. And now I have to say also goes to Halifax, and that's represented by an h. So then we would put an and goes to Halifax, right? Good. Okay, I'll count the brackets after we stick this in. But you can see here what we've said is there is at least one x, so some, where that x is good, that x is a human, and that x goes to Halifax. So let's bring that in, and then I'll count the brackets. Oops. Copied the whole thing instead of just this. Okay. So what do we have here? This is bracket on that, bracket on that. This is bracket on that. And this does not need a bracket. Okay. And you can see perfect match, right? And you can see, you know, there is some x's ranging over all of this. This is all the same thing because it's one x. It's just not named. Could be any individual thing who is good and a human and goes to Halifax. This is just saying at least one of the things, the x's, which are good, a human, and goes to Halifax. Okay. Let's do a mixed one, shall we? Let's do number 11. It's the trickiest one, so it's good to explain it, I guess. But you should also do the practice on your own, ideally. Afterwards, walk through this yourself after. So what do we have here? Well, we have a if then as our main operator, which is good. And we'll see actually that the quantifier here is just ranging over the good dogs that go to Halifax, right? It's not ranging over Carl and Egbert who go to Halifax. It's within this if-then claim, and so it's only talking about good dogs going to Halifax, not Carl and Egbert going to Halifax. So interestingly, we will have this inside our if-then claim, right? I guess first let's translate. Yeah, it's probably easier if we just translate this arrow claim first, right? And then we'll put brackets around our parts. Okay, good. So let's start with this left half. So we have every good dog goes to Halifax, right? Well, every is like all, right? It's a universal quantifier. So we're going to use our all x. So for all x's, and then we know that we're talking about this phrase here, this like subphrase. All right. So then we're saying, what are we saying here? For all x's, if x is good and a dog and goes to Halifax, then this. Okay. So we can do a big and chain here, right? So we're going to say is good is G. So if x is good and x is a dog, which is F. So we're going to say F, X. Let's bracket this section off so we don't have a bunch of ands building together. Then we'll say X is good and a dog and goes to Halifax. Or I'm sorry. Yes, so we're saying if every good dog goes to Halifax, not everything is good and a dog and goes to Halifax. So this is actually an arrow. It's saying, you know, if it's a good dog, it goes to Halifax, then Carl and Egbert go to Halifax. So this is actually an arrow. So we'll say like this, goes to Halifax is H. Okay, and I'll clean up the brackets after. Okay, so now we've done this side. Here we have, for all x's, for every x, if x is good and a dog, then x goes to Halifax, right? Okay, so now let's do the right side. Carl goes to Halifax and Egbert goes to Halifax. Well, in this case, we're just talking about specific people, which is little c and little e for Carl and Egbert. And goes to Halifax is H. So in this case, you know, it's saying Carl goes to Halifax and Egbert goes to Halifax. So then we can translate this down. So we'll have goes to Halifax for Carl, and that's what this is. Goes to Halifax for Egbert. That's what this is. Great. Okay. Good. Okay, now I'm going to have to fix up the brackets when I import this in. All right, so let's see how our brackets are doing. This closes with this. Actually, let's start from the inside. This closes with this. This closes with this. Okay. This with this. This with this. This with this. And then that with that. Okay, great. So that looks good. So as you can see here, we have if, all of this is on the left of the if then, right? So we have if for everything, if it's good and if it's a dog, it goes to Halifax. Then Carl and Egbert go to Halifax. Carl goes to Halifax and Egbert goes to Halifax. So let's see if this is correct. Oh, I must have the wrong amount. Ah, yes, I should not have had this bracket on the end. Okay. That's when it says it's ungrammatical. First thing to do is check your brackets. Okay, so I deleted the bracket at the beginning, and you can see perfect match. Carnap is happy with it. Yeah. Okay, so that's some practice. Walk through it. See how I did it. Do the rest of the practice, and of course, do problem set 15 in chapter 11. Thanks for watching. There's one more lesson in this course. So pay close attention to it. We'll be doing one more lesson on predicate logic again, but this time with some derivations in predicate logic, which I think is pretty cool. So keep an eye out, and I will see you then for the next and final lesson.